Hi everyone. So yeah, that's kind of weird. I don't know why it's saying only one. Let me take a look here. It's actually bouncing around between one and two. It's okay. I mean, as long as you guys can see me. It just seemed like a very strange thing. So, um, well, today I just wanted to do a quick problem. I'll only take half an hour. I promise I won't go over like I did that one time. I want you to see me actually do a problem together and answer any of your questions if you have any questions about the problems in the assignment. Solving these problems is a little different. It isn't just a matter of plugging into an equation. There's actually more conceptual procedure, and so they're a little bit difficult, which is why I changed the format a bit. There's more of a learning curve. So we spent last week just going over some pre-recorded videos, and this week, I'm just doing these live streams. Okay, and I'll only do half an hour because I do have that other video for you to watch. And also, I just want to comment that forces is very important for people that are in ESS or PT. So this physics is getting much closer to being relevant to your field, especially if you go into kinesiology. Okay, but as the course goes on, I'll just point these things out. Let's do this problem here. So right now we're just going to do one problem in three parts, and it's just a single block on an incline plane. On Thursday, I'll do a problem where I have like two blocks connected by a string, which is a little bit more complicated. Okay, so what I have here is a 10 kilogram box on a plane inclined at 45 degrees, and the coefficient of kinetic friction. Kinetic means it's going to be moving. Okay, kinetic friction is 0.35, and what is the net force, and what is the acceleration? Okay, and all right, so how do you approach these problems? All right, so I'm not going to go over all the justification for the steps. That's kind of the point of the pre-recorded lectures, which I assume you've watched by now. I'm just going to sort of go through the steps, okay? And so let me switch to my other whiteboard here like this, and the very first step is to draw the picture and draw what you would physically see, and you're actually going to do this in the lab. So yeah, that's worth thinking about carefully. Okay, you're going to do an experiment very much like this, and so here we have an inclined plane, and the angle in here is 45 degrees like that. So we'll draw that in there, and we put a block on that like this. All right, here's our block. Well, not a very good block, but good enough for now, okay? And that's what we would physically see. So this is the first step. The second step is to identify all the forces that are acting on this object, okay? And I would recommend that you start off with gravity as the first force. And draw a little dot in the middle of the box. For these problems, we don't care about the extension of the box, okay? We'll worry about that later in the course when we do rotational motion. Technically speaking, gravity acts everywhere on that box. It doesn't just act at the center. But for these problems, it's sufficient to just think about all the forces that are acting at the middle, okay? Now, gravity, technically speaking, acts straight down like that. Okay, but I wouldn't draw it like that to start with. For these problems on an inclined plane, I would recommend that you immediately start off by breaking up gravity into its two components: the component which is parallel to the plane and the component which is perpendicular to the plane. Okay, and that's because you have to get F net. F net is a vector sum, and so to do that, it's best to kind of form that characteristic cross. Okay, and so let's get rid of that, and let's just replace it right away with the perpendicular component like this, which is calculated using the formula mg cosine theta. All right, and the parallel component of gravity, which is mg sine theta. Okay, now why it turns out to be mg sine theta. Now, why it turns out that cosine is perpendicular and sine is parallel, that's part of the pre-recorded lecture. I went through that geometry. It's probably best to just memorize this, okay? And you could go through that logic again and again and again, but like in a test or in an assignment, why? If you've kind of convinced yourself that it works, once, it's going to always work. Okay, so we'll just memorize that the perpendicular component here, that's the cosine, and the parallel component here, that's the sine. Okay, and so there's your first force. Now I won't put it in the numbers here because it's kind of hard to write on this whiteboard. I'll do that in the other thing, but that's your first force, so gravity. So immediately write it in terms of those two components. Those two components are totally equivalent to the gravity acting straight down. Okay, in fact, you're going to have a lab on this. Okay, you're going to have a lab where you have a force table, and you're going to apply like forces, and then you're going to break up the forces into their equivalent components, and you're going to see that the two components actually add up to the original force. Okay, so there's your first force. Let me see in the chat here. Everyone's good. Okay, so now it's saying 4, so better. All right, so that's your first force. The other force is the normal force. Whenever you've got two surfaces touching, that's normal force. I'll do that in red. Okay, so see, these are the two surfaces that are touching here. Okay, like that. And perpendicular to those two surfaces, that, like, see if I drew a line there, perpendicular to that would be like straight out like that. Okay, so perpendicular to those two surfaces, there's your normal force, Fn. All right. And in this particular problem, I also have friction. And the way friction works is if the whole thing is moving down here like that, so there's the velocity, it's sliding downhill, then there's going to be a frictional force. I'll do that in green, and the frictional force will be uphill. So the frictional force is always opposite the velocity, okay? And we'll call that one FF like that, all right? And if you read the problem, you think about it, there are no other forces. Okay, and so you've identified all the forces. Now, if you look at that, you could see why we broke up gravity into those two blue components there. Okay, because if you turn your head sideways, what you're going to see is you see this characteristic cross. And the way this works is, let me, I guess, use purple here, is you see the two forces that are opposite one another, that is the parallel component of gravity and the force of friction there like that, they compete like a tug of war. They compete independently of the other two forces because the other two forces are perpendicular. Okay, whoops. Let me redo that. Okay, like that. And these two forces, the normal force and the parallel component of, the perpendicular component of gravity and the parallel force here, they also compete. Okay, and they compete independently of the other two forces. All right, and so that's why you want to eventually get it into this characteristic cross like that. All right, so at this point, so you've drawn this diagram. At this point, you're going to evaluate each of these forces in turn. Okay, again, start with gravity, and to do that, it's kind of hard to draw here, so I'm just going to switch back to my other one like that. Okay, and let me do here the parallel component of gravity. All right, so the parallel component, that was the one that was the sine, and so we're going to have here mg sine theta, and let me cut and paste my theta from right there. There we go. All right, so mg sine theta, and m, that is 10 kilograms. All right, G, technically 9.8, but we're rounding off to 10 just to make life easy for ourselves. And it's sine of 45 degrees like that. Okay, and if you work that out, it turns out to be 70.7 newtons, like that. Okay, the perpendicular component, I'll just round that up, like that. That's going to equal mg cosine theta. Okay, like that. And if you work that out, it turns out that the cosine is also equal to 70.7. Sine 45 degrees and cosine 45 degrees are equal. At 45 degrees, sine and cosine are equal. Okay, so like there's some special sines and cosines, like sine of 30 degrees is a half, cosine of 60 degrees is a half, and sine and cosine of 45 degrees, they're like 0.707, or they're equal to 0.707, or if you multiply it like by 100 here, you get 70.7. Okay, so there are those two values, and at this point, let me switch back to the diagram. And what you can do is, when you solve these problems, I mean, you're gonna do a little bit of drawing, then you're gonna do a little bit of math, and then you can do a little bit more drawing. So back here in the diagram, we can actually put those numbers in here. We can now start writing in that this is equal to 70.7. newtons, and this one is also equal to 70.7 newtons. Okay, like that. All right. Now the next thing is, don't lose sight of where we're going. We're heading towards this F net, okay, which is the net force. All right. So that's where we wanna eventually get. Okay, and because it's a vector, there are two pieces to it. There's the piece which is parallel like this, okay, back and forth, like that, and there's a piece which is perpendicular like that. Okay. Now, in this problem, there is no acceleration, there is no motion perpendicular to the plane. And so what you could say is that the normal force and this component, the perpendicular component of gravity, they have to cancel. Okay, this is just conceptual. Why? Well, it's actually Newton's law, Newton's second law. Suppose that Fn is bigger. Okay, so suppose Fn were like 71 and this is 70.7, even just a little bit bigger. Then what would happen is that this thing would lift off the inclined plane, because Fn would beat the perpendicular component and would lift it off. That doesn't happen. Okay, and what if the other one won? What if the perpendicular component wins? Well, then it would start to dig into the inclined plane. That can't happen. Okay, that's not happening. Okay, and so neither of those two things are happening. And so what you have to conclude at this point is that the normal force also has to be 70.7 newtons. Okay, so there's no real equation for that. All you're doing is conceptually saying, well, that has to cancel that, because otherwise it would, it'd be moving like perpendicular to the plane, and it isn't. Okay, and so because of that, these two have to equal one another. All right, and so we could go back to our screen here, our other whiteboard, and we can say that Fn, I'll write it like that, that also has to equal 70.7 newtons. Okay, and then finally there's the frictional force, and you say, well, how do I get this frictional force? Oops, sorry, right over here. Call it FF like that. How do you calculate that? Okay, and that's where this coefficient of kinetic friction comes in. Now my second part B, is about the static friction and kinetic. They both are friction, but they act so differently, and the way you deal with them is different, which is one of the reasons I wanted to do both of them in this problem. That really watch for this word kinetic versus static. Okay, so this is kinetic friction. For kinetic friction, what you do is you multiply the coefficient of kinetic friction. You multiply that by Fn, the normal force, like that. Okay, and that's going to give you the force of friction. All right, when it's kinetic, and so if we multiply those two together, we're going to have 0.35, and that's a dimensionless number. Okay, and you're going to have the normal force, 70.7 newtons, like that. And when you multiply the two together, I forget what it's equal to, so turns out to be, looks like it's equal to 24.7. 24.7 newtons, like that. Okay, and now we can go back to our diagram here, like that, and it was equal to 24.7. So I'm doing friction in green here, so this is going to equal 24.7 newtons. Okay, all right, so now perpendicular, they cancel, but think of it as a tug of war. But now parallel, these two do not cancel. Okay, the component of gravity downhill is beating the friction uphill. Okay, if the friction uphill would win, it can't happen because friction can't be that big. But if it did, then it would start going uphill. Okay, but the component of gravity downhill is winning, and so it's going to start to accelerate downhill. All right, and you say, well, how much does it accelerate downhill? It's the difference between the two. So the two are competing. This is pulling 70.7 down. This is pulling 24.7 up. And when you subtract the two, what do you get? I guess 46. Okay, and so that's how you figure out what the net force is. Okay, there's no net force perpendicular, but the net force parallel is going to be 70.7 minus 24. All right, so let me switch back. So over here, you can say that F, let me write it like that, is going to be the parallel component downhill, 70.7, minus the friction uphill, like that. And that's going to equal 46 newtons. And I guess you could even say downhill, like that, okay? Because it's this one that wins. It's the gravity downhill that wins. Like if we were to put directions on this, I'm probably covering that. Oh, you can see it a little. Downhill, like that. All right. Yeah, it's covered up a bit. Okay, like you could say, that the parallel component is downhill, and the frictional force, which way is that? Uphill. Well, which one wins? Well, obviously, gravity downhill wins, and so it wins by 46 newtons downhill. Okay, so there you go. That answers the first question. That answers what is the net force, and the answer is 46 newtons downhill. Okay, so let me see if there's any questions in the chat here. I know there's a bit of a delay. All right, doesn't look like there's any questions so far. All right. Okay. So now the next question is, what's the acceleration? And for that we have to use like, why did we get the net force? I know I asked for it, but why is the net force so important? And the net force is so important because of Newton's second law. Newton's second law basically says F net is equal to ma. I mean, some people say F is equal to ma, but I always like saying F net, and you should probably memorize it that way and think about it that way, because it's not any one force, it's the sum of all the forces. So it's F net, all of the forces added together. That's what this was all about. All of that work to find all those individual pieces was so that we could find F net, okay? And then once you got F net, that's got to equal ma. Okay, that's how it relates to the acceleration. Now we want to find A. We have F net already. There it is. And we have m, and so A is equal to F net divided by m. Okay, like that. And so that's 46 newtons divided by 10 kilograms, and that gives us 4.6 meters per second squared. Okay, there you go. That answers the question, what is the acceleration? All right, so there's an example of a problem of a block on an inclined plane where it's moving and you have friction, and so it's kinetic friction. Okay, and I think this is like, I'm not don't remember exactly, but I think this is your first problem on the assignment. Okay, so it more or less follows this pattern here. Okay, so the next part of these that I wanted to answer, or that I wanted to demonstrate, was what do you do when it's static friction? And static friction, you have to think about it very differently. Because it's static, it's almost like you have to do the whole problem all over again, but backwards. Because it's static, nothing is moving. Okay, and if nothing is moving, that means that the acceleration is zero. And so it's almost like you're starting at the bottom and working up rather than starting at the top working down. Okay, so here we have that it's static, and because it's static, the acceleration is zero, like that. Now if the acceleration is zero and we have that F net is equal to ma, well then obviously F net must be zero because acceleration is zero. And that means that all the forces have to cancel. Okay? And that's what's different than the previous problem. Let's go. Let me show you the diagram again. If you take a look at the diagram here, not all the forces are canceling. Okay? So once again, the perpendicular forces, that is the normal force up, or perpendicular, or I guess that way, is canceling the perpendicular force of gravity into the plane. Okay, so those are canceling, but the parallel are not. Okay, and because they're not, you're getting motion. So now you've got a different situation. Okay, so let me start the diagram all over again. Not that everything's totally different, but it's probably best, when you have a change of a situation, to just quickly resketch the diagram. And this is again 45 degrees here, like that. And here's your box, like that. And first force we'll do is gravity. There's that component here, like that. and that component like that. Okay, and this is still mg cosine theta, whether it's moving or not. So whoops. So the values don't change because m is the same, g is the same, theta is the same. The only thing is that it's not moving, and so this is going to turn out to be 70.7 newtons. Ooh. All right, and then this one's mg sine theta. And if you calculate that, that's going to be 70.7 newtons like that. Okay. And okay, that takes care of gravity. And again, because m didn't change, g didn't change, theta didn't change, there's still the same values. Okay, here's our normal force. And there's also a frictional force, but it's a different frictional force now. So instead of FF, let's call it FS for static. Oh, forgot the N right here. Okay. And now, before or in the previous problem, we wanted to calculate Fnet, but now we have the conclusion or the assertion that Fnet is 0 to start with. So we're starting with Fnet equals 0. And that means that all of these forces have to cancel. All right, so just like last time, we argued that, the forces this way, perpendicular, they have to cancel. And so, yeah, this has to cancel this one. And so this one must equal 70.7. That's the same reasoning as before. Okay? Like that. But now we have the same situation here. This one has to cancel that one. And so that tells us that Fs has got to equal also 70.7 newtons. Okay, and you can see that that's a different value than before. Before we had, I think it was 24.9, and now we have 70.7. In fact, all of these are 70.7. All the components are 70.7. Okay, so that's what changes. As soon as you have static friction, I mean, you're kind of starting from this. Rather than trying to find Fnet, you're starting from Fnet equals 0, and you're seeing what that implies in terms of all the components of the forces. Okay? So let's switch back to the other whiteboard. Let me see the chat here. No questions so far. Good. All right. And so what that basically says is that we have, well, we still have this. Okay, those are still true. And you know what? We can just make life a little easier to read. That's still, that's still 70, and that's still 70 like that. We have that the normal force, that's still 70.7. Okay. What changed was here we had FF was equal to 24.7. Now we have F static friction, and that's also going to equal 70.7 newtons. Okay. So in answer to the question, what is the force of static friction? The answer is it's 70.7. Okay, so there's that. Okay, and now what? Well, the next thing was show that the coefficient of static friction is actually given by tangent of theta. All right. Now, if you go back to the pre-recorded lectures, I actually proved this. I actually proved that for inclined planes, that the force of static friction is actually tan theta, and it's not exactly given by, so that's poor wording. What it actually turns out is that the coefficient of static friction is greater than or equal to the tangent of theta, like that. Okay, so this is another big difference, which usually causes confusion. Whereas up here, when we calculated the force of friction, I mean, it was an equality. You just took the coefficient of kinetic friction, you multiply it by Fn. Here, it's not an equality, it's an inequality. And that means that you don't really get the value of the static friction, you get its minimum value. It could be bigger than that, but you get the minimum value. Okay. Now, the definition, so we're going to show that that's true, at least in this problem. The actual definition is this, okay, or the actual original equation is this: force of static friction divided by the normal force like that. Oops. Okay, so the coefficient of static friction is bigger than whatever the ratio is for Fs over Fn. You know, I can't tell you what its value is going to be, but as long as it's bigger than this, it won't move. Okay. Now those numbers are easy to work out because they're both 70.7. Okay. So the static friction is 70.7 divided by the normal force. That's also 70.7, like that. And of course, that's equal to 1. Okay. So basically, what this is saying is that the coefficient of static friction has to be bigger than 1. It could be 2, it could be 3. It could be 70, it could be a million, whatever, okay? As long as it's bigger than 1, the block is not going to slip. If it's less than 1, then it will slip, okay? That's all this is saying. So it doesn't actually uniquely specify what the coefficient of static friction is. It just says what range it has to be in. It has to be bigger than 1, okay? Well, is that 1? Can you get that 1 from this equation here, tangent of theta? Well, tangent of theta, if you put in 45 degrees and you do this on your calculator, yeah, it works out to 1. Okay, and so like I actually proved this, and we didn't really reprove it, but we at least demonstrated that it works even in this that it works in this particular problem. Okay, so you know, like in the assignment, I also have a problem like this. You don't have to redo all of this analysis. You know, like you could just use tangent of theta, and sure enough, it'll give you that. Sorry, it'll give you the coefficient of static friction. All right, but it's nice to see that, you know, you could use this procedure and you will get exactly what you expect. All right, so what I've given you up till now is covers about half of the assignment. All right, what it doesn't cover is, you know, problems where you have two blocks that are connected by a string, and I'll go over those on Thursday. Okay, so we'll do some problems with probably a couple of problems where we have like two blocks and they're attached by a string, and we'll do those kinds of problems. They're a little bit more involved, but this should get you at least going. And don't forget, if you're doing the assignment, and start it right away, because it's like 25 questions. It's longer than any of the previous assignments. You know, if you're doing the assignment and you get stuck, even if you navigate away from the page, you can close the page and come back later. It'll just say resume the quiz, and you can resume it. And I've tested this. I've like literally gone days and then come back to it, and it allows me to go back and continue the quiz. So don't worry about that. And if there's a problem, of course, just let me know. Okay. So that's it for today. It's a shorter live stream, because I also want you to watch that other video on Kepler's laws, or on Newton's universal gravitational law, and so do that for the rest of the class. But if you have no questions, then that's the end of the live stream. Okay, so let me just ask in the chat. We can end this. Okay. All right. I hope this was helpful. Okay. I mean, I don't just want to throw pre-recorded lectures at you, because I do want you to see, you know, I do want you to see me actually solving these things. But all right. If that's it, we'll end the chat, or we'll end the live stream. And of course, there's always the Google Hangouts in the evening if you want to ask questions. Bye-bye.